Hey everyone, welcome back to TechUniversityTutorials, the place where complex computer science concepts become crystal clear. Today, we're diving into one of the most clever algorithms in all of computer science, Huffman coding. Now, you might be thinking, Huffman coding? What even is that? Well, here's a fun fact. Every time you open a zip file, view a JPEG image, or listen to an MP3, you are already using Huffman coding. Mind blown, right? So sit back, stay focused, and by the end of this video, you will fully understand Huffman coding. From scratch, step by step. Let's go. So first things first. What is Huffman coding? Huffman coding is a lossless data compression algorithm. Lossless means when you compress the data and later decompress it, you get the exact original data back. Nothing is lost, not a single bit. The core idea is simple but genius. Instead of giving every character the same number of bits, which is what ASCII does with its fixed 8 bits per character, Huffman says, why waste bits on rare characters? Let's give shorter code to common characters and longer codes to rare characters. So it's all about being smart with your bits. This algorithm was invented back in 1952 by a brilliant student named David A. Huffman, and it's still used today in zip files, JPEG images, MP3 audio. Everywhere. Let me show you the problem with the old approach. Imagine we have a string, ABRACADABRA. With standard ASCII encoding, every character takes 8 bits. So 11 characters times 8 bits gives us 88 bits total. But look at this. The letter appears 5 times. The letter C appears only once. Why should both A and C get the same 8-bit code? That's a huge waste. Now, with Huffman coding, we assign code based on how often the character appears. A is super common, so it gets just 1 bit. B gets 2 bits. Gets 3 bits. And the rare ones like C and D get 4 bits. When we encode abracadabra now, we need only about 23 bits. Instead of 88, that is more than 73% compression. Incredible, right? Before we jump into the algorithm, let's get 4 key concepts clear. Concept 1. Frequency table. This is simply counting how many times each character appears in our input string. If it appears 5 times, its frequency is 5. Concept 2. Priority queue or Min-Heap. This is a special data structure where the element with the smallest value always sits at the top. We'll use this to always grab the 2 least frequent characters first. Concept 3. Binary tree node. In Huffman coding, we build a binary tree where every leaf node represents an actual character. Internal nodes just hold combined frequencies. Concept 4. Prefix codes. This is a magic that makes Huffman work perfectly. We guarantee that NO code is a prefix of another code. This means we can decode without any ambiguity. Going left adds a 0. Going right adds a 1. Got all 4? Great. Now let's build the actual algorithm. Here's the Huffman algorithm in 5 clear steps. Follow along carefully. Step 1. Build the frequency table. Scan your input string and count how often each character appears. Step 2. Create leaf nodes. For each unique character, create a node that stores a character and its frequency. Step 3. Insert into Min-Heap. Put all those nodes into a Min-Heap or priority queue. The node with the lowest frequency will always be at the top. Step 4. Build a tree. This is the core step. Repeat this until only 1 node remains in the heap. Extract the 2 node with the smallest frequencies. Create a new internal node whose frequency is the sum of those 2. Make them the left and right children. Insert the new node back into the heap. Step 5. Generate codes. Once the tree is built, do a DFS traversal. Every time you go left, append a 0. Every time you go right, append a 1. When you hit a leaf, you have the Huffman code for that character. Simple, right? Let's see this in action with a real example. Our input string is abracadabra. Let's count frequencies. A appears 5 times. That's our most frequent character. B appears 2 times. R appears 2 times. C appears just 1 time. D appears just 1 time. So our frequency table is A equals 5, B equals 2, R equals 2, C equals 1, D equals 1. Now we put all these into our minute heap, sorted by frequency from smallest to largest. So it looks like C equals 1, D equals 1, B equals 2, R equals 2, A equals 5. The smallest ones, C and D, are right at the top, ready to be merged first. Let's build the tree step by step. We start with our 5 nodes in the minute heap. C equals 1, D equals 1, B equals 2, R equals 2, A equals 5. Merge 1. Extract C with frequency 1 and D with frequency 1. Create a new internal node with frequency 1 plus 1 is equal to 2. This new node has C as left child and D as right child. Put the CD node back in the heap. Heap is now CD equals 2, B equals 2, R equals 2, A equals 5. Merge 2. Extract CD equals 2 and B equals 2. Create new node CDB with frequency 2 plus 2 is equal to 4. CDB goes back in the heap. Heap is now R equals 2, A equals 5, CDB equals 4. Wait. Resort R equals 2, CDB equals 4, A equals 5. Merge 3. Extract R equals 2 and CDB equals 4. Create our CDB node with frequency 2 plus 4 is equal to 6. Back in heap. Heap A equals 5, RCDB equals 6. Merge 4. Extract A equals 5 and RCDB equals 6. Create the root node with frequency 5 plus 6 is equal to 11. Only ONE node remains in the heap. That's our root. The Huffman tree is complete. Beautiful. Look at this tree. Now let's generate our codes by traversing it. Starting from root. Go left to reach A. That's just one move. So A equals 0. That's 1 bit for our most common character. From root go right, then left to reach B. So B equals 10. 2 bits. From root go right, right, left to reach R. So R equals 110. 3 bits. 4C. Right, right, right. Left equals 1110. 4 bits. 4D. Right, right, right. Right equals 1111. 4 bits. Notice how A, which appears 5 times, gets the shortest code with just 1 bit. And C and D, which appear only once, get the longest codes with 4 bits. That's the genius of Huffman. It perfectly matches code length to character frequency. Now let's see how encoding and decoding actually work. Encoding is super easy. You just look up each character in your Huffman code table and replace it with its code. So AB becomes A is 0, B is 10. So the encoded string is 010. That's just 3 bits instead of 16 bits in ASCII. Amazing. The full string ABRACADABRA becomes 0, 10, 110, 0, 1110, 0, 1111, 0, 10, 110. 0, that's only 23 bits total versus 88 bits in ASCII. Now for decoding. And this is where prefix codes shine. Start at the root. Read bits one by one. 0 means go left, 1 means go right. The moment you hit a leaf node, you found your character. Write it down. Then jump back to the root and repeat. Because of prefix codes, no code is the start of another code. So there's 0 ambiguity in decoding. You always know exactly when one character ends and the next begins. Let's talk efficiency. The complexity of Huffman coding. Building the frequency table takes O(n) time, where n is the length of your input. Building the minute heap takes O(k) log k, where k is the number of unique characters. Building the tree itself also takes O(k) log k, because we do k1 merge operations and each one involves inserting back into the heap. Generating the codes is just a DFS traversal. That's O(k). So overall, the time complexity is O(n) plus k log k. In practice, k, the number of unique characters, is at most 256 for ASCII text. So the k log k part is essentially constant. That makes Huffman incredibly fast for real-world text compression. Space complexity is O(k) for storing the tree and the code table. And now, the fun part. Where do we actually see Huffman coding in the real world? Zip and gzip files. The deflate compression algorithm at the heart of zip actually uses Huffman coding as a key step. Every time you zip a folder, Huffman is working. JPEG images. When your phone compresses a photo, Huffman coding encodes the DCT coefficients that make up the image data. MP3 and AACII audio. Huffman is used for entropy coding of audio samples, helping shrink your favorite songs without noticeable quality loss. MPEG video. Movie and video codecs use Huffman tables to compress frames efficiently. HTTP2. When you browse the internet, HTTP2 uses HPAC, which includes Huffman coding to compress HTTP headers. Faster web browsing? Thank Huffman. PDF files. Huffman streams are embedded for compressing font data and images inside PDF documents. So this is not just a theoretical algorithm. It is everywhere in your daily digital life. Alright guys, let's wrap it all up with a quick summary. Number ONE. Huffman coding is a greedy, lossless compression algorithm. Number TWO. It assigns shorter binary codes to frequent characters and longer codes to rare ones using a binary tree. Number 3. It uses a Min-Heap or priority queue to efficiently build that tree by always merging the two smallest nodes. Number 4. The time complexity is O(n plus k log k), super efficient in practice. Number 5. Its use in ZIP, JPEG, MP3, HTTP2, PDF, everywhere in the real world. And that is Huffman coding, completely demystified. If this video helped you understand Huffman coding, please give it a big thumbs up. It genuinely helps this channel grow and reach more students like you. Subscribe to Tech University Tutorials and hit the bell icon so you never miss a new DSA lesson. Drop your questions or topic requests in the comments below. I read and reply to every single one. Until next time, keep coding, keep learning, and I'll see you in the next video. Take care.